reason we're talking about water is because water is important. In fact, the control of water is related to economic and government and military power, and this has been known for a long time. In fact, in the social sciences, there's a whole hydrology theory of civilization, that water is the basis for civilization, that once you have a city-state of a couple 100,000 people, you have all the specialized labor and skills you need, so there's no reason to go to civilization larger than a city-state unless you need millions of people to build a massive waterworks. Not all anthropologists agree with that, but at least some people have this idea that water and civilization go hand in hand. In fact, in China, the Chinese word for politics, Shangji, includes a character that looks like 3 drops of water next to a platform or a dike. Here are the drops of water, 1, 2, and 3. So there, the word politics and water are related. And I know that's true in California, and it's definitely true in Texas. So we see politics and military and government and water and civilization go hand in hand. And certainly the Romans knew this. Romans had a vast empire, and they used water infrastructure as a part of this empire, massive aqueducts like the Pont du Gard in the south of France. That's no longer a working aqueduct, but some of the Roman aqueducts still work. They still move water. The Romans lined some of their aqueducts with lead. Turns out that was a bad idea, but they did move water, and it was part of controlling the fringes of the empire, so to speak. And you can walk across this. It's about 150 feet high, and when I went there when I was 12 and I walked across it, my mom was like, go ahead, it's okay, there's no handrails. And I made it there and back. And I was scared because it's only a few feet wide and you're really high up. And then some French mother with a stroller was there. So the intrepid French mothers are hard to scare, I suppose. That's a part of their infrastructure and a part of the Roman power. And we also have these water temples in the middle of Cambodia. The Khmer Empire built Angkor Wat, which a lot of people think is a religious temple, actually a water temple in the middle of a water complex. And only crazy societies build temples to water, right? Like the Khmer Empire and Californians. You have water temples up near San Francisco. So that's a part of this. We celebrate water in different religious ways and as a part of our power and our empire.
He was nothing. The well is everything.
Just 2 clips. That says it's a 3.5-hour movie. I didn't want to play the whole thing. So water is a big part of the Arabian Peninsula in the unity of the different tribes and clans and groups, and he just shot someone who drank from his well, and he goes, he is nothing. The well is everything. The well is everything. Water is everything for society. Here's another way we can think about it.
Water's precious. Sometimes it can be more precious than gold.
I guess I could have just said it. This is a Treasure of the Sierra Madre with Humphrey Bogart, and that was Walter Huston. Does anybody recognize the name Huston from filmmaking? That movie directed by his son, John Huston. John Huston, movie maker, is the only movie maker to direct his father and his daughter, Angelica, in Academy Award-winning performances. So you're going to learn some movie history here too, I guess. And this is a great movie. I recommend you go watch both these movies because they got great clips, and water is a part of it. And I'm going to show some more clips from both as they go on. They're in the desert looking for gold. Don't waste your water. Water is more precious than gold. And this is true for society as well. So water and civilization go hand in hand. That's the good news. What's the bad news? The bad news is sustained droughts are correlated with collapsed civilizations. In fact, Jared Diamond wrote a book, Collapse, How Societies Choose to Fail or Succeed, where he looks at a map of collapse over time. And the collapse of society is often predated by ecological strain, often water-related. Of course, Brian Fagan wrote a book, The Great Warming. Great book, great author, what a gem of society. I've been quoting him for years about climate change and the rise and fall of civilizations, about the relationship of water with civilization. When we had warming before, good for Europe, bad for Mesoamerica. Is that what's going to happen next time we have warming? Who knows? But we see that water strain and collapse is correlated. New research just a couple years ago in Science magazine about the 3 of the 5 multi-century Chinese dynasties, the Tang, the Yuan, and the Ming, all collapsed at a time coincident with multi-decade drought. They went to a cave in the Gobi Desert at the western reach of the monsoon, and there are stalactites in the cave. Remember, stalagmites grow up and stalactites hang down or something? I'm an engineer, so forgive me. But there are these things that hang down from caves that have mineral deposits. And they become a year-over-year record of how wet that year was. And if you take this beautiful stalactite and chop it down, and then count the rings, sort of like we cut down a beautiful tree and then see how old it was. It survived everything except for us chopping it down. Anyway, you take the stalactite and you count the mineral layers, essentially. You can get a year-over-year record how wet the year was. And the Chinese have been keeping spectacular written records for thousands of years. We can overlay this with their written records and find out that at a couple periods where you had a couple decades of drought, 3 of the 5 multi-century Chinese dynasties collapsed. Now, that doesn't mean drought caused a collapse, but the correlation in time with collapse and drought is interesting, to say the least. Similar kind of research comes out a little later about the Roman Empire, looking at caves in Europe and finding a similar kind of water strain coincident with drought and the collapse of the Roman Empire. All of us in the 3rd grade learned it was the Visigoths and the Ostrogoths and the Vandals and the Lombards that invaded that ended the Roman Empire. But it might have been these Teutonic tribes were invading because of water scarcity at the fringes of the empire. So a correlation there as well. Certainly the Mayan collapse is the classic collapse of a civilization. I can't remember, it went from like 1 million people to 100,000 people in the span of a couple decades. That's a pretty fantastic collapse of civilization, and a lot of people suspect that's related to drought. And then the Khmer Empire in Cambodia peaked in 13th century. Great feature on that in the National Geographic, July 2009, where they have maps of the water system and the Angkor Wat photos. If you want to learn about water in these temples, go read the National Geographic. This kind of collapse is spectacular. For a society to essentially disappear, the only modern day equivalent we have that comes anywhere close is Detroit, which has gone from 2 million to 400,000 in the span of about 4 or 5 decades. So Detroit's collapsing right now, we might say. But that's not water-induced, I don't think. It might be something else. And at the same time, Detroit collapses, the suburbs are thriving, so maybe that's not a very good example. Anyway, it's hard to imagine a civilization collapsing, but they happen periodically, and water is often correlated with it. So energy and water are what I would say are the most important things for this century and beyond. So if water has been the critical element forever, energy and water have been critical for the last 150 years and moving forward. It's not just water anymore, it's water and energy. They're the two looming crises of the 21st century, and Time magazine tells us to be worried, be very worried. We have when the rivers run dry, water, the defining crisis of the 21st century, the high cost of cheap coal, oilaholics, that's Uncle Sam and Chinese dragon running out of water, unquenchable, America's water crisis and what to do about it. And if you thought peak oil was a threat, what about peak water, right? So these are not happy books. They're not saying that we're all going to be fine. These are kind of negative. These are there's a crisis language, a crisis mentality around both resources, and they're both important. And then here's the idea. We're trying to squeeze the earth to get our energy out of the gasoline nozzle. And look what that gasoline nozzle is connected to is a water hose dripping out the back. We're squeezing the water out of the earth to get energy out of it. Can we solve both simultaneously? And we'll see. I guess that's part of the challenge. Now I'm going to talk about water for a second. Keep in mind, I'm an energy engineer. I'm a mechanical engineer. I'm making it up on the water stuff. I know there's a lot of hydrologists in here. Correct me later so I don't get embarrassed, but I'm going to talk you through the hydrological cycle just in case you're like me and you had to learn it. Basically, there's one cycle. It's pretty massive. It's global. This is a picture from Science from 2006 that shows the fluxes and storage of water. And there's a lot of numbers on here. I'm not going to quiz you, but there's arrows that go up and arrows that come down, and there's numbers. And those numbers are the flux in 1,000 cubic kilometers per year, a flux of water up or a flux of water down or across. Then there are numbers in boxes, like in the sea or the groundwater. That's the storage of water in 1,000 cubic kilometers. That's not a flux, it's just an amount that's stored there. And what we see is actually there's a pretty complicated cycle. There's a lot of flows up and down and around, and there's actually a lot of water. There's plenty of water. That's the good news. There's a ton of water, but it's in the sea, or it's in the glaciers and the snow, or the groundwater, or the permafrost. So the water is just in a place that's inconvenient, below ground or top of mountain, or a form that's not drinkable, like seawater. Very little of it is in the river. Very little of it's in the wetlands or other places that we can reach easily. So this hydrological cycle picture shows you how powerful the water cycle is, how there's plenty of water. It's just in the wrong form or the wrong place, or in some cases the wrong time. For example, in Bangladesh, they get all their water in 1 month in the monsoon season. And so the energy implication is we spend energy to move it to the right place or the right time, or to get it to the right form that we can use. That's the energy implication of the water cycle. And this is the same chart, but a different form. This is from Liquid Assets by the RAND Corporation. The world's water is on the left, 97.5% of salt water, 2.5% is fresh water. Of that 2.5% that's fresh water, you have permafrost, rivers, lakes, swamps, groundwater, ice, and permanent snow cover. A very small fraction is easily accessible, clean, surface river water or lakes. A very small fraction of the world's water is what we like to drink and in a form that's easy for us to reach. That's the challenge. The other remaining 99.5% or whatever it is in total requires energy of some sort. So that's just prologue. The three main points I want you to remember are that energy and water are interrelated. We use energy for water and water for energy. The energy-water relationship is already under strain, and constraints in one sector create constraints in another. It is cross-sectoral. An energy outage leads to a water outage and vice versa. And that we have some trends that mean this will be worse. We have 4 trends: population growth, which increases total demand; economic growth, which increases per capita demand. We have more people and they get richer, or at least remember we used to get richer. Well, we might do that again, and that will increase our per capita demand. And then the global climate change intensification of the hydrological cycle has energy implications as well. And then policy shifts, where we are actually choosing to move towards more water-intensive energy and more energy-intensive water. And I'm going to talk most about the policy shifts because I think that's interesting after I give you some background information. All right, so about energy and water interrelated. Here's one. So Treasure of Sierra Madre again. I'll show you how we use water for resource production. This is just an excuse for me to buy movies on my UT gift account and then watch them at home.
Open the sluice gate!
They're using water to leach out the gold, and that's real. That's sort of the way it was done in California in the 1840s and 50s, but still done today. In fact, this picture shows how energy and water are interrelated. By the way, that was one of Humphrey Bogart's best performances. You got to watch that movie. This picture sort of shows a society, and in the upper right is a catchment, a reservoir with water, and it collected from the rain or the runoff, whatever, and that water is spun through turbines in the dam to make electricity directly. So there we're using water for electricity, hydroelectric power. Then that water goes downstream and is actually pulled into the power plant here, a thermal power plant. In that case, the water is used indirectly for thermal power production to cool the power plant. Then that water goes downstream. And then you have arrows that are blue for water flows and arrows that are red for energy flows. The blue flows show where the water is going, and the electricity flows in the red. And we have a neighborhood here where electricity goes up here. We see someone watering their lawn, watching TV, washing their clothes, and there the washing the clothes uses water and energy at the same time. And then we have water being pumped up to the city. Look, there's electricity going to these pumps and to these pumps to move the water. So we're using electricity to move the water to the cities and the residential neighborhoods. And we're using electricity to drive the pumps for the irrigation for the farms. And by the way, here's the mine that uses water not only to leach out the materials, but might have runoff that affects the water quality here. And then we have electricity coming to the water treatment plant here, which gives us fresh water with reverse osmosis membranes here, and that water goes up to drink to different places. And then this is our wastewater treatment plant, where we put the wastewater treatment plant at the lowest altitude we can find in the city, because the solid laden flows of wastewater are heavy to move uphill, so it's easier to move them downhill. Water's hard to move uphill too, but you'd rather move the solids down. So we put that in the lowest spot we can find in the city. We treat the water, the wastewater, we put it back in the river, and let the next city drink it, which is kind of funny. Actually, it turns out our water treatment plant is downstream from the wastewater. That's not very good design. I would say, normally you put your fresh water intake up here rather than there. Well, that's okay. Well, it's just art for this case. But we have these water systems require a lot of energy, and the energy systems also require a lot of energy. It turns out the energy sector uses a lot of water. In fact, the thermoelectric power sector is the largest user of water in the United States. It is responsible for 48% of the total water withdrawals, which include fresh and saline water, and 39% of the freshwater withdrawals. That's for cooling the power plants. It works out that for every kilowatt hour of electricity that's generated in the United States, anywhere between 0.2 and 42.5 gallons of water was withdrawn for cooling the power plant, of which 0.1 to 0.8 gallons was consumed. So in this room, over the course of the hour that we're in here together, we'll probably use 5 kilowatt hours of electricity or something for the projection and the cameras and the air conditioning or HVAC systems and the lights. And those 5 kilowatt hours might be responsible for anywhere from, I don't know, 0.5 to 5 gallons of consumption, but maybe hundreds of gallons of water withdrawn, depending on whether we get power here from the nuclear power plant in the state or some other power plant. So a lot of water is used for us in this room, beyond what we're drinking, just to cool the power plants to make the electricity. And by the way, we also need water for production and refining transportation fuels. And just to give you a sense of scale, these water systems are quite large. That's a picture of a cooling tower in Michigan City, Indiana. That's for a coal plant. A lot of people think cooling towers are just for nuclear. That's actually for a coal plant. So you can use cooling towers for coal or natural gas as well if you want. And they're quite large. It dominates the landscape. This is like a picture from The Simpsons or something with the cooling towers in the background. So the energy sector uses a lot of water. And it's because of the cooling. There are 2 main cooling approaches. Open loop cooling on the left, where you take water in from a river or lake, you cool your power plant and you return it. Or on the right, where you have a closed loop cooling with a cooling tower, you take water in, you recirculate it until you evaporate it. In the open loop system, most of the water that's withdrawn is returned. You take water out of the lake or river, you cool your power plant, then you return it. You don't really consume much, but you use a lot. And with a cooling tower, you withdraw much less, but consume almost all of it. So if you care about withdrawals, then you want to use a cooling tower. If you care about consumption, then you use open loop cooling. So it's not always obvious which one is better. Open loop withdraws more, consumes less. Closed loop withdraws less, consumes more. So this is one of the conundrums facing water planners and energy planners. Turns out it breaks down the amount of water used depends on what type of technology you're using. On average across the nation for thermoelectric power, the national average is something like 21 gallons of water withdrawn for every kilowatt hour generated, of which half a gallon is consumed. But it actually varies a lot by whether it's once through cooling or not. With a cooling tower, you only withdraw 1 gallon but consume all of it. With open loop cooling, you withdraw 40 gallons but only consume a quarter of a gallon. Oh my gosh, then it varies by fuel. Wait till I get to the next chart. And then hydroelectric, I put that on there as well just as an example. When you build a reservoir to hold water for a dam, you've increased the surface area over the run of the river. And in the west, where you have large surface area exposed to the sun, you lose a lot of water to evaporation. And on average, across the nation, we lose 18 gallons of water evaporated that would not have evaporated per kilowatt hour we generate from the electricity from dams. And that number varies a lot from 0 in the northeast, where there's not much evaporation, to 75 gallons of water per kilowatt hour in the west. So our water consumption in this room might be much worse than what I told you if we're getting our power from one of the major western dams. So there's a lot of water consumption used for electricity, and it gets more complicated. It depends on the fuel and the cooling technology. Nuclear is at the top. Nuclear is the most water intensive, followed by solar thermal, by the way. Oops, that's a black eye for solar thermal. Then coal, then natural gas combined cycle. The natural gas combustion turbines are leaner. Then solar PV and wind don't use much water. So how much water to use depends a lot on the fuel and the conversion technology, whether it's combined cycle or open cycle, and the cooling technology. So there's no easy answer for this. It turns out, in total, we consume vast sums of energy on water. Here I am with my 2 sons. This is me. This is my son, David, who's a skateboarder dude. And this is my son, Maverick, who's hiding. And this is my dog, Waterloo. And this is in Austin, Texas, and we have public restrooms there that use the highest quality drinking water you can find for the toilets. This is actually typical in America, although I used your toilets earlier and you don't do it here. So congratulations to you. I enjoyed my toilet experience. Thank you for using your water again for the toilet. But we use incredible water to flush our toilets. And it's free. That's a free public restroom, by the way, and a free public fountain. I paid for it through taxes and bonds, but I don't pay at the point of use, so it's free at the point of use. This is my dog. He has his own drinking fountain because it's Austin, and Austin loves dogs. My dog gets better drinking water than probably 6 billion people, maybe 4 billion. And I'm actually proud of that. My dog deserves good water too. Why not? But I think those billions of people who don't have it probably would like it too. And I think that's sort of interesting. And by the way, my dog doesn't have to pay for that water either. So I think it's interesting. In total, Texans consume anywhere from 135 to 150 gallons of drinking water per person per day in the residential sector, not including commercial and industrial, in our homes. 135 gallons per day is San Antonio, because San Antonio has massive water crisis. 250 gallons per day is Dallas, where they have huge lawns that they irrigate. So we consume a lot of water per person. It's lower in California. You tend to irrigate, well, in the residential sector, you irrigate less. In the ag sector, you irrigate more, so maybe it balances out. But we use a lot of water per person per day, and it's something like, I don't know, 25 to 50 million BTU per person per year or something. And then water's often free or cheap at point of use. So this is the challenge, right? We have the greatest water in the world, but we spend a lot of energy to get there, and we give it away for free, essentially. That's one of the challenges. If we look at the energy for water, it comes from a variety of sources for a variety of purposes. It's a busy chart. You might have seen charts like this by Lawrence Livermore for energy flows, where they show energy on the left and where it goes to for residential, commercial, transportation, that kind of thing. And this is my first attempt at doing a water flow diagram on energy for water. And this is just the public supply. This does not include industry. This does not include agriculture. 5% of our nation's energy just goes to the public supply. If you add in industry and ag, about 15% of our national energy consumption is for energy. I mean, it's for water. So think about that. We don't really think about water conservation as energy conservation, but it is. We use coal, natural gas, petroleum, nuclear, renewables, and other to make electricity. So we use a lot of energy for electricity, and that electricity goes for pumping water, moving it, treating it, heating it in commercial sector, heating it at home. We spend 2 quads of energy, 2 quadrillion BTU, or 2% of national energy consumption is just heating our water at home once we've already moved it there. That's a big number. That is more energy we spend heating water in our homes than Switzerland uses in a year for all purposes. More than Sweden uses. So that's a big number. And by the way, residential water heating is pretty easily done through solar thermal, say, at least in most places. And then here's wastewater collection and treatment at the bottom. And then here's the water services at the bottom, and all this is rejected energy. A lot of that energy is lost as waste heat. And we could use that waste heat to start doing our water treatment if we designed our systems better, but we don't. So that's just the public supply. It's a pretty busy, messy thing, but that's a lot of energy flowing for water purposes. And then if we add in the industrial ag, it's another 5 or 10% on top of that. And by the way, just that That public supply is responsible for a couple 100 million metric tons of CO2 emissions a year. About 5% of our national carbon emissions is just from the public water supply. Big number. Then California is a more extreme example. 19% of its electricity is on water, primarily for end use, but also for conveyance in some places where you move the water over mountain ranges. And it's a similar story wherever water is scarce. So we use a lot of water for energy. We use a lot of energy for water. Those are the points I'm headed towards. If we look at the numbers, the amount of energy we use for water and wastewater treatment, collection, conveyance, and distribution, we see a range here. So I showed you before gallons of water per kilowatt hour. Now I'm going to show you kilowatt hours per million gallons, because we use kilowatt hours to treat our water for the pumps and things like that. Clean surface water needs about 1,400 kilowatt hours per million gallons to pump it from the river, treat it a little bit, and move it to your home, say. Now that number varies from 0 in New York, where it's gravity-fed water that's already clean, to much higher if you're in San Diego. Groundwater is more expensive from an energy perspective. You have to pump the water up from below ground to the surface and then treat it and distribute it. Brackish groundwater is a higher energy range because of the total dissolved solids. Seawater is even worse because of the salts. And then you have wastewater is another 1,000 to 2,000 kilowatt hours per million gallons. And the point here I want to show you is that this wastewater treatment, even the most advanced wastewater treatment, 2,000 kilowatt hours per million gallons, is a fraction of the energy for desalination. And desalination is an order of magnitude more energy intensive than freshwater. Desalination is energy intensive and carbon intensive. And if we reclaim the water, we just use this wastewater, instead of pumping it into the river, we reuse it. We can avoid a lot of carbon energy in some situations. We can do that. Wastewater treatment requires energy. It's a part of what we do. A book I recommend you read is The Big Necessity, The Unmentionable World of Human Waste and Why It Matters by Rose George. She's a British author. She's really hilarious. She goes around the world and watches people poop. And then she writes about it. It's a great bathroom book, actually. I'm not kidding. You should read it in the back. But you read this, and there are a couple lessons that come out. First of all, societies that are healthy and wealthy have sanitation. Societies that are sick and poor have no sanitation. And whether they're healthy, wealthy because they have sanitation or they have sanitation because they're healthy, wealthy isn't exactly obvious, but the correlation is uncanny. People who are rich and healthy deal with their mess and their waste, and if they don't deal with their waste, they become sick and poor, sort of the way I walked away from it. So we need to deal with our sanitation. In that last chart I showed you, where if we go back one, the energy for reusing our wastewater is less than desalination. We could do that, but it grosses us out. We could do reclaimed water. We could use that advanced treatment, but it grosses out because that's toilet to tap. We don't want to use our toilet water and put it back in the tap. What we do is we dump it in the river and let the next tap use it in the next city. So we already kind of do this, or we put it in the aquifer and then drink it, and then it's okay. So it grosses out to drink our toilet water, but it turns out they already do it in Singapore. Something like 20% of the water that in Singapore is the new water program or reclaimed. And on the International Space Station, they use reclaimed water because water is too expensive to ship to space. So they have to reclaim it. Now there they reclaim the gray water from the urinals and the sinks and showers, but not from the toilet. So they don't recycle or reuse the black water, but they can reuse it and it's fine. In fact, you can go to NASA at the gift shop and buy a bottle of reclaimed space shuttle water. That's kind of astronaut urine. But it's been treated, it's okay. And I think they charge you extra for it, is the funny part. I actually did my PhD research on this. So my final PhD project at Stanford was on an ammonia sensor that I use for emissions monitoring. And we tested on the bioreactor NASA was building because when you treat the gray water, there's a lot of ammonia and urea in there that comes out, and you can measure the ammonia off-gassing to measure the health of the bioreactor. So in the late 90s, early 2000s, I was doing final tests on the bioreactor, and it didn't launch till a year and a half ago. So this is a slow development process. But astronauts are strong and healthy. They do it. We can do it as a society, even if it grosses us out. All right, so that's just energy and water. Energy is used for water. Water is used for energy. It turns out that relationship's already under strain. We have water constraints that can become energy constraints. We have heat waves, where you have thermal pollution limits that can constrain power plant operation. We have droughts. We have water scarcity that can prohibit power plant operation or fuels production. If you don't have water to grow your bio crop or your energy crop, or you don't have water for your power plant, say. And so water can constrain energy, and energy can constrain your water. Blackouts disrupt water treatment and distribution, so I'll go through a couple of examples. There was a record heat wave in France in 2003. I don't know if you remember this. It killed about 15,000 people in France, about 35,000 people across the continent of Europe. It was a killer heat wave. It was a massive heat wave. And so the demand for air conditioning was spiking because people were literally dying from the heat. So the demand is spiking for energy. And at the same time, the rivers in France were so hot The nuclear power plants, many of which are on rivers in France, could not get the cooling they needed because of thermal pollution limits. So the way it works is the river temperature is here, and you put it through your power plant, and you can return it at this temperature. It gets hotter as you return it. But as the river temperature gets hotter, you get less cooling capability between the two, but you can't return it hotter because that's a thermal pollution limit. You can't return the water above a certain temperature because it will cook the critters in the river. You get boiled escargot right there. So they limit the temperature, you get less cooling. So they actually had to dial back the power plants by 15% in France as the power is spiking. So here, a water constraint through a heat wave actually became a power constraint, and people were dying as a consequence. So this was a high-impact event. And this isn't some third-world country, right? This is rich Western France, and this was a problem. Then you can also have droughts. We had droughts a few years ago in the southeast near Atlanta. Droughts could close nuclear power plants within days, say power companies near Atlanta. Interestingly enough, Atlanta was still allowing people to water their lawns when this was happening. I think this is fascinating. The Lake Lanier was dropping, and the intake pipe for the nuclear power plant was about to be surpassed. And that's not a dial back 15%, that's a hard stop. If you don't have the water for nuclear, you turn off the plant. We all know that nuclear wants a lot of cooling. We want to give as much cooling as it needs. And this is a real problem. They almost had a hard stop. They came within a couple of days, and they've had nuclear power plants turn on and off over the years because of droughts. It actually led to some tension and civil war potentially between Georgia and Tennessee. You had a legislator in Georgia who went to the floor of the Capitol and said he found an old map from the 1800s that suggested the boundary of the state should be a mile or two further north into Tennessee, which conveniently would have claimed the Nickajack Reservoir and all this water for Georgia instead of Tennessee. So we had like a land grab going on from one state to another. And I don't mean Georgia, Russia, Georgia. I mean Georgia, America, Georgia, trying to do a land grab with Tennessee. The Tennessee legislators were hilarious. They said, well, we'll settle this on the football field because there's a great rivalry there, which I thought was funny. So we have states suing each other. There's like a 3 or 4 state lawsuit in the Southeast. Kansas sues Missouri. All the western states are suing each other. So there's all sorts of lawsuits and tension between this. And that's one of the other things about water that you should know, that it's something worth fighting over. Here's a classic saying, whiskey is for drinking, water is for fighting over. It's an American West proverb. A lot of people attribute this to Mark Twain, but that's a false attribution. He didn't actually say it, but somebody said it, and it's a good saying. Let me play for you a video of water conflict.
Are you with that party of dogs who are drinking at my well?
Yours.
Who is he? Tapas!
He is dead.
Yes. Why?
This is my well.
I have drunk from it.
You are welcome.
There's always water conflict. We've had so many water wars over time. The 1960s Arab-Israeli war, the Six-Day War, people say it was a water war. It's about diversion of the headwaters of the River Jordan, not a religious war, a territory war, a water war. These are the claims people make. So we think of water resource conflict as a part of this. We can see that around the world, not just in the movies, although the movies are better at predicting this than we think. And then here's a Western conflict. Las Vegas running out of water means dimming Los Angeles lights. This is the reservoir between Hoover Dam, and that white ring is where the water used to be. It had dropped something like 100 feet in 6 years. If it drops another 50 feet, then Las Vegas could lose its water intake, and Hoover Dam stops generating electricity. This is a good snowpack year. We'll have a good snowmelt year, so the water might come back up this year. But this is a challenge. We have an energy water scarcity happen at the same time. And this is a classic. This happened. We have dams in South America that just, you have to choose between having water for drinking or water for electricity sometimes. So this is a challenge. And then here's something where a power outage at my house actually ruined my water. I just took a photo of this with my iPhone. Boil water notification. That was yesterday. My wife called and said, we have to boil our water because we had a power outage at our house and it took the power out at our well. And keep in mind, I live in an urban area in the middle of Austin and I'm on well water. It's just a unique neighborhood. We have 95 homes on well water. Works out, power went out, the pumps went off, the treatment system went off, so the water might be bad, so we have to boil our water, which is easy for us, we just turn a knob. But if you're in Africa and you have to boil water, probably your daughter walks 5 miles to pick up fuel wood, and she's at risk of getting raped or abducted, walks back, then she walks another couple miles to get the water, then has to boil it. So for us, that's still easy, but it's hard in other parts of the world. And this is a challenge. A energy constraint became a water constraint, even in Austin. And that's one of the challenges. I thought that was hilarious. Like, you got to give me that statement. I'm going to use that in my talk tomorrow. This shows the energy water crisis as it's happening. And trends imply that this relationship is going to be exacerbated. The strain is going to be exacerbated because of all our different trends. So we have energy for water, water for energy. We have straining the relationship and trends driving it to get worse. So let me tell you about the water system that I'm on, the well I'm on, and it's expensive. So this is the Ridgewood Village water system. I live in the middle of a 1.25 million person urban area, and I'm on a well water. We have 95 homes on this well. It basically goes down to the 1960s. The architect who developed the area, developed the neighborhood, designed the home that my parents bought that I bought from my parents, he was an asshole. And the local water people didn't want to sell him water. It basically just goes down to that. So he said, I'll drill my own well. So he drilled a well, and he designed 95 homes, so we're all on the well. And to this day, the water company still won't incorporate us because they hate him so much, and he's been dead a decade. This is very fascinating to me. But so his daughter's been trying to sell the well, but they're still mad at her because of his father or whatever. This was all built in the 1960s. It had non-standard pipes. This guy, the architect, great designer, not great water system builder, used oil field pipes, used whatever pipe he could find. And as he built a house, add another section, 12-inch, 14-inch, 16-inch, 8-inch. Every pipe length is different diameter. PVC, metal, wrought iron, like crazy stuff. So it's a horrible water system. And we're on well, very hard water. We have a house filter and a filter on my fridge, and the water's still too hard for my wife. I don't mind because I grew up with it. I don't know any better. But she's been exposed to good water before, so she's not as interested in drinking it. And it's a substandard system, and we've been trying to sell our water system as a group of 95 homes to the local city water people, and they finally forgive us for the sins of the architect in the 60s and are willing to buy us and hook us up to surface water, so to aquifer water. We're on a sensitive aquifer, so we're under all sorts of restrictions. And they'll get us on surface water. It'll cost $1.9 million to rebuild the system. That's $20,000 per home. But I don't have $20,000. They said, that's okay, you can pay on your property taxes $165 a month for 20 years, which works out to almost $40,000. And that's not including the water bill, by the way. Water bill is another $50 on top of that, say. That's incredible. That took us 5 years of negotiation with every mayor we could find to get this deal done. And we're like a rich, educated part of town with lawyers and doctors, and we get together to yell at each other. If we have one holdout who refuses to be part of this, and the water district required 100% compliance, and one guy's holding out, so we're going to make him pay twice as much, I think is what we figured out. But anyway, he's convinced it's a government conspiracy. This is just our little tiny rinky-dink water system, $2 million. Imagine trying to rebuild the entire water system in America. We built the water system in America 100 years ago using iron that lasts 100 years. And then we did another big build-out 50 years ago with stainless steel that lasts 50 years. So if you do that math, they're both collapsing together right now. And people imply and calculate this is $250 to $750 billion is needed to rebuild the water system across the nation. That's a lot of money, but we'll do it. What else are you going to do? And there are other trends: population growth, economic growth, climate change, policy choices all make it worse. And a lot of this has to do with quality water. We have more people who are getting rich who want more water. As people get rich, what do they want? They want meat and they want electricity. And meat and electricity are very water intensive. And then climate change makes it harder, and then we have these policy choices that make it trickier. And then the quality of our water is getting worse. So what do? It doesn't matter. There's this proverb, any water in the desert will do. I think this is my last clip, I promise. We'll see how it goes.
Good? It's all right.
He finally gets to water at a well, and it's just all right. It's brackish water, the high level dissolved solids. In the desert, any water will do. And actually, this is sort of an allegory for the whole world. We're going to more degraded, lower forms of water now. And this has an energy implication. As we run out of the easily accessible, clean, fresh water, we go to worse forms of water that are further away. This has energy implication. So we're moving towards more energy-intensive water. We have stricter water wastewater treatment standards. We need to clean the water up more. That has an energy implication. We're going deeper into the aquifers of wells. That means more energy to raise it up. We're going towards desalination, to take salted water and desalt it. In fact, worldwide capacity is expected to double in the next few decades. In a place like the Middle East, where you have a lot of energy but no water, so people trade energy for water, or in London and San Diego and Texas and other places, long-haul pipelines and interbasin transfer, where we move water thousands of kilometers from one river to another, like the South-North Water Transfer Project in China, the largest water project in the world, just surpassing California's State Water Project. And so you have a lot of these big projects that take a lot of energy. That's a choice we're making. We're choosing to go to more energy-intensive water. And we're choosing to go to more water-intensive energy. If for a variety of reasons we want domestic energy, renewable energy, low-carbon energy, so we're going towards things like nuclear power and solar thermal, both of which use more water for cooling than other sources of electricity. We're also choosing water lean forms like natural gas, solar PV, and wind. So it's a mixed story on electricity. But if we look at transportation fuels, the future of transportation fuels are especially thirsty. Unconventional fossil fuels like oil shale, tar sands, things like coal to liquids have 2 to 4 times worse water quantity demands than conventional petroleum. Natural gas is actually better from a water perspective in terms of water quantity if you use natural gas compressors, but if you use electricity compressors, electricity-driven compressors, then your water impacts are higher. Electricity actually needs more water. I love electric cars, but they need more water than gasoline. Hydrogen can be worse if you make the hydrogen with electricity. And biofuels are the poster child for bad water behavior. They need something like 1,000 gallons of water per gallon of fuel. And this is much different than petroleum, which needs something like 2 gallons of water per gallon of fuel. That doesn't mean we shouldn't do biofuels. It just means we should think about the water impacts before we go into it completely. So we have this choice we're making to go to more water-intensive energy. In fact, we have a federal RFS, or renewable fuel standard, that essentially mandates an increase in water consumption. This chart shows on the left axis billions of gallons of water per year that's used for transportation fuels production for the different years from 2005 to 2030. And we see that we need a couple 100 billion gallons a year to produce our petroleum gasoline. This is water at the wells and water for cooling at the refineries. And then on top of that, we've added a mandate for E10, ethanol 10 with corn grain, irrigated or not irrigated, for E85 and E10, and here's the cellulosic ethanol. These biofuels and other fuel standards have basically mandated an increase in water use for liquid fuels production to the tune of trillions of gallons of water per year. To put that in perspective, we consume 36 trillion gallons of water a year in the United States. A couple new trillions of gallons will have to be consumed for biofuels. That's a big number. And we've gone into this energy policy without considering the water policy implications. And that's where we get a train wreck. Our energy planners assume they have the water they need, and our water planners assume they have the energy they need, and they actually sit in different rooms and don't talk to each other, and they're regulated differently, and they have different congressional committees that oversee them and fund them, and they make decisions like this. There might be a lot of reasons to do biofuels, but we got to figure this out and go to a low water intensive biofuel form, something better. Cellulosic's obviously better than corn. So we have other options available we might consider. And this is the challenge. So I'll close there just with sort of one final comment that sort of sets the stage. I think we'll have time for Q&A. That's a lot of bad news I've shared with you, but there is good news. The good news is that energy conservation and water conservation are synonymous. So that's great. If you conserve water, you will conserve energy. If you conserve energy, you'll conserve water. In fact, if your goal is to conserve energy, you might conserve energy faster by conserving water. And if your goal is to conserve water, you might get there faster and cheaper by conserving energy. I think my daughter sums this up. She and I brush our teeth together every night, and she said this a couple of years ago. When we brush our teeth together, we turn the water off, like we get our toothbrush wet, and then we turn the water off to brush our teeth, and we turn the water back on. By the way, that doesn't save much water, just so you know. You should do it, but it really doesn't make much difference. If you really want to save water, don't water your lawn. But anyway, turn the water off when you're brushing your teeth, and we do that. And I didn't turn the water off fast enough once. Like I brushed my teeth, and I didn't get the water off fast enough, and she got real exasperated. She turns it off and sort of huffs at me. She's like, turn the water off, Daddy. The scientists need time. As one of these sort of dramatic, like, whose kid are you, right? I think it sums it up that conservation buys us time. It might not be the ultimate answer for everything, but it sure does buy us a lot of time. We get some good solutions. So that's the good news. And I'll close there. I'll be happy to take some questions. Thank you.
Michael, talk to us a little bit more about federal policy and this ships passing in the night, crafting energy policy that is in turn creating a water problem and pursuing water problems that are in turn exacerbating our energy strains.
So the policy making structure for water and energy is very different. They're in a variety of ways. On the energy side, there are very strong federal agencies, Department of Energy, USDA, Department of Defense, people who have a strong level of engagement on energy. So we have a top-down structure for energy, and water is the other way around. We have very strong local water agencies, county, city, state, that kind of thing. So the direction of decision-making is inverted for the two, and that's one of the ships passing in the night. Energy policy is made without thinking about water because they don't think about water at a federal level. There's no one in charge of water at a federal level. EPA thinks about water quality. There's not a single agency that thinks about water quantity that's in charge for it. The United States Geological Survey does surveys, or at least they used to. They would measure how much water we use at a state level, and that's about it. But we don't have anyone sort of watching to make sure that we have enough water for our decisions. So there's an inverted structure. Then the decision-making is done in different committees in Congress and in different agencies on the presidential administration, and they don't sit in the same room. And they have different assumptions, they have different budgets. Energy R&D is separate from water R&D and this kind of thing. And so they're just not even aware of each other until the last couple of years. You mentioned about the last decade. The last few years, the policy structures have gotten together. California is ahead of everybody on this. California energy water planners have been talking and publishing since 2005, but talking longer than that. Texas has got into it about 2 years ago. Other states are starting to happen. California's in the lead. And that's not really happening at the federal level, although Senators Bingaman and Murkowski in the Senate Energy Natural Resources Committee have written legislation called the Energy Water Nexus Integration Act that asks for a study and trying to examine this question. And I think it's interesting. So the challenge with the quantity question, so if EPA already looks at quality, the quantity question is it's under a local decision-making authority. If you ask a city planner, hey, what's your plan if you have a drought and don't have enough water? The city planner will say, we'll go to that reservoir there. But 12 other cities have also said that's their plan nearby, and that reservoir doesn't have enough water for those 12 cities. So you need, therefore, a basin planner, and some states have a basin planner or a state planner. You need a state to help you because the cities can't think big enough to take care of it. So that's fine, unless you have a river that crosses state boundaries. A lot of them do. And then across the state boundaries, what do? Well, then we have two states talk to each other, or you have a compact get formed. So you have compacts get formed, but sometimes those states don't like each other and they sue each other, and sometimes they still divide the water up by political boundary instead of by water boundary. Instead of drawing the water basin by the water's natural flow, they divide it by political boundaries. And then what if you have an aquifer like Ogallala that spans 7 states, however many states it spans? So there's actually a role for federal engagement because some of these water bodies are too big for one state to handle. And the federal government actually doesn't pay attention right now, but maybe they'll start. So I think that's part of the ships passing in the night. The good news is there are some staffers on the Hill who are really on this issue, and they're trying to push it through. We'll see what happens with Congress, but there might be some studies at least, so there might be something happening.
Are you aware of any systems or any ways to recycle the brine water after the reverse osmosis?
So if you have a reverse osmosis plant, you have a water stream with high dissolved solids. It comes in, you get fresh water out, and you get another stream with even more dissolved solids going back, your briny water stream, your wastewater stream. And the question is, what do you do with that, or are there systems to deal with it?
That's what you do.
Yeah, so the most sophisticated process we have so far is you dig a hole in the desert, dump it there, or you dump it in the ocean. So far, that's been the approach. And that actually can work to some degree if you do it in the right way. But there's a challenge. When you desalt water, you get saltier water as a consequence for at least one of your streams. And in Saudi Arabia, where they've been spending a lot of energy on water for the last few decades, desalting, they have returned so much briny water into the Persian Gulf, the salinity levels of the water near the Gulf edge of the Saudi Arabia have actually gone up. So they've actually raised the salt content of the water near the edge, which means they have to spend more energy getting rid of the salt, and then they have an even saltier stream in return. I don't know of any great ways to get rid of it. You can burn stuff, you can burn the salts and that kind of thing, evaporate it out, get rid of it, but this is always tricky. If you're in a desert climate, it's a sensitive place to be doing it. So I don't have any good technological solutions in mind other than maybe to do it less, is what I would say. And that's one option. And the other thing you could do is if you're going to desalt, you're going to desalinate, you could incorporate or integrate it with other systems. So what they do in Abu Dhabi is they have power plants that have waste heat, and they integrate their water treatment and desalting with the power plant, and the waste heat saves them a lot of additional energy because it starts the desalting process. So that doesn't fix your brine stream problem, but does spare you some of the other environmental problems from the energy implications for treatment. The interesting thing is, because they need so much more energy in the summer for air conditioning in Abu Dhabi, they have more waste heat in the summer. They therefore have more water in the summer. And what do you do with the water? Well, you grow golf courses instead or something. So you might ask whether that's a reasonable thing to do in Abu Dhabi. But so they have more water in the summer as a consequence. And in the winter, they don't have enough waste heat for the water they need to drink. So they turn the power plant on just to give them water. So maybe that doesn't always work. But you can do integrated systems that helps. But with the brine stream is always a weak point for desalination. I'm not aware of what to do with it other than bury it, re-inject it, or get it deep into the ocean somewhere else. But I'm sure there might be someone else who has a better answer in the audience than me.
A lot of people use RO systems at their home for water treatment, and there are products, I picked one up at Costco, that is 100% recycling with the waste going back into your water system. It's a very interesting system we might apply here on campus. So there's zero waste because you're only using a few gallons of water, and so that's increasing the total dissolved solids just a very small amount for all the other water you use in the house.
Have you, or do you know if anyone's developed a methodology for calculating energy use for a project such as the one you're describing on replacing aging infrastructure? So sort of like how to calculate ahead of time. Because it seems like, you're talking about the cost, but then I'm also thinking like energy cost on that.
So is the question like, what's the energy cost of the aging infrastructure, not just
or just in general, a method of calculating energy cost for a project. I don't think people are used to thinking about that. They're used to thinking about financial costs. And so I'm wondering if someone has looked at how do you figure energy costs, and then how broad of a net circle do you draw to calculate those for a given project?
So I think the aging water infrastructure, the financial cost is easier to calculate, and the energy or carbon cost is harder to calculate, so we don't agree on how to measure that. But there are several, I'm not going to answer. I'm going to answer two other things that I know how to answer, so that I'm going to dodge that question. But there are two things I think about with the aging infrastructure that are energy and carbon related. Something like 15% of our water doesn't make it from the water plant to our homes and businesses because the system's so old it leaks. That means 15% of our energy and carbon for treating and distributing that water is wasted. So that's one part, that if we improve the infrastructure, that might have an energy or carbon benefit because we have an aging infrastructure with leaks. That's one issue. The other issue I think of with our infrastructure, if we're going to rebuild it, we don't have to replace it with the same design, big centralized plants with long pipes. We can actually go to a more distributed water system, distributed rain barrels and harvesting and things like that, that might change the way we do water. And it might depend on where you are and what kind of elevation changes you have, whether this makes sense. But you could do water treatment at a neighborhood level or a more distributed way where you don't spend as much energy pumping water around. The challenge being there is some economies of scale with energy. Larger plants can be more efficient, but then you spend so much energy moving the water, you might lose it. So if we're going to redo the infrastructure, we could think about more distributed water as an analog for distributed energy where you might get resiliency out of it. If that one water plant goes down, no one has water. If you have 100 water plants and one of them goes down, well, they can get water from the neighbors. So that might be a model we consider going forward as we rethink the infrastructure. And a part of that calculation should be the energy and carbon, I think.
As Professor Wilkinson has pointed out often in his water class, U.S. water law was established before and after the Civil War when the population west of the Rockies of non-native peoples was approximately 1.2 million, and today that population is 87 million, but the applicable federal laws remain the same. So to get a sustainable, comprehensive long-term solution, where is the leadership going to come from to make that happen?
Yeah, that's great. So the water law in America is, there's no one law, there's many laws. There's roughly Western water law, designed before there were non-natives and without natives' rights in mind, I would say. And then there's Eastern water law, and Eastern water law is roughly, don't use more than you need. And Western water law is, use everything you can find, but ask me first, I'm the central authority. And then you have 5 states that have a hybrid system, and Texas is one of them, where we have riparian Eastern rights and Western central allocation rights as well. So we have 50 states and a couple dozen different water rights and law systems. And I guess the most updated ones are probably 100 years old or something. I think of the California and the Western water law to be a very old conflict until I go to Hawaii. And in Hawaii, that's a 2,000-year-old conflict. That's a very old sort of discussion where water means a whole lot of things to different people. But I think there's a challenge where if our legal, policy, regulatory frameworks don't adjust with the times, and the times might be new technologies, there might be new weather patterns, they might be new resource assessments, they might be new population patterns. If they don't adjust for the time, then we're gonna have a disaster, and I think that's actually what we got right now. So where we're gonna get the leadership from? Probably the Western states, because they feel the pain the most. And I think the Eastern states don't dive into water law. I don't think they care. It's just, that's not their biggest problem. So I think a lot of the problems are actually caused by the Western states senators many decades ago will probably be solved by Western state senators. And in fact, that's why Senator Bingaman from New Mexico cares a lot about this. That's why Murkowski thinks about it. Murkowski in Alaska has an abundance of water. She has a different problem. She wants to find a use for it. And Bingaman has a scarcity. So I think we'll see leadership from the West. It might take some real extreme shortages. In Australia, they've had an incredible drought. And they finally, a few years ago, said, you know what, we're going to redo it. And they redid the water rights and the water markets and things like that. And it took a pretty extreme, endured, long drought to finally have them scrap the system, start from scratch. But I guess that's what it will take here.
Firstly, I'm wondering, in an era of increased distantiated production of fresh water, meaning that we get our water from very far away, is it important to sort of foster an emotional connection to water resources as a means of promoting water efficiency? And secondly, I'm wondering, with reference to the South-North Water Project, how that will affect international relations with countries in South Asia in the near future.
Wow, those are great questions. Okay, so first question is, what if we had a more personal connection with water? Would that be an important part of a water program or whatever? I'm paraphrasing. In this idea actually shows up with energy and food as well. So we waste a lot of food in America. We have a couple quadrillion BTU of energy embedded in the food we throw away each year. So we have more energy in the food we throw away than Switzerland consumes in a year. So that's a number. And one reason people suspect we throw away so much food is because we didn't have to make the food. If it was our own farm, we wouldn't waste it because we know exactly how much effort goes into it. And we're so detached from the food system, we throw a lot of it away, and food's so cheap and so easy to get that we don't have this connection with it, and therefore conservation of food doesn't make sense. And I would say the same idea is applicable for energy and for water. The water, I turn a knob and it comes out. I didn't have to dig the well by hand. I didn't have to push the water through the membranes to treat it. I didn't have any connection to the water at all other than some bill I get once a month that costs $40 or something that's completely affordable. It's not very expensive, and as much water as I want comes out of the tap. So that disconnection might be part of it. And so there are a lot of cities, and Austin's one of them, I'm sure you do a lot in California, are pushing for rain barrel and rain harvesting programs to actually establish a personal connection. Meters that actually tell you how much water you have. Most water meters are behind the house, underground or behind the rose bush. You can't read it. But if they give you a meter inside the house that tells you how much, you get a personal connection with the water that way. I'm not saying we should all dig ditches necessarily, but I do suspect that having a personal connection to the water would make us be more thoughtful and conserving of it. I think that's a good idea. I don't know how you establish that because water is inherently infrastructure related. So that's one question. Next question is international relations and water, especially with China. I think international relations and water is not just a China problem, it's a global problem. We see it in the Middle East for sure. I mean, the Israeli-Palestinian peace tension is partly driven by water tension. Water is a big part of that discussion in ways that we in America don't really recognize, I think. Then you have the Rio Grande River Rio is Spanish for river. In Texas, we call it the Rio Grande River, which is like big river, if you call it that. Anyway, so we have the Rio Grande River in Texas, which is one of the most contested international water bodies in the world. We have treaties with Mexico that dictates how much water Mexico has to leave in the river for us, and we violate the treaty all the time and don't think twice about it. They violate the treaty. We fly spy satellites over Mexico and take pictures of them using the water in the fields, and we say, you're using too much water, you're violating the treaty, and then senators from Texas go over and meet the president and say, if you don't stop this, we'll invade. So it actually gets quite tense. Portugal and Spain have this problem. North Korea has dams and rivers that share with South Korea. You have this issue where dams will be opened to cause a flood to go downstream and kill people. That happened with Korea and the Korean Peninsula. So I think the Chinese incident, that's just one more on a whole list of international relations that'll be tense. I think so I'm not sure if that particular incident, what's going to happen. If it starts to affect, I don't know what river would be affected by the South North River. Would the Mekong be affected? Do you know?
Brahmaputra, the
So
Mekong, there's 7 major rivers that come out of that region.
And there's millions of people who live on that well, they've already dammed it up enough that the backward flow of the river's already stopped, is that right? Mm-hmm. So the Mekong is one of the, I guess the only river in the world that flows backwards for a while, for a section, is that right?
Well, we have the San Joaquin here, we do that.
Well, okay. So there's a section in South Asia where the river flows backwards, and that's an important part of the ecosystem, but because of the dams in China, that's stopped, I think, is that correct? So my guess is, so I've taken a long walk to say, yeah, it's gonna be a problem. Because I think we should stop there.
On that cheerful note, let's thank Michael. Very nice presentation.